Hi, and welcome to our fourth set of videos on building a simple electronic structure program in MATLAB. In this video, in this series of videos, we're going to talk about the Coulomb operator. And in particular, we're going to talk about building our nuclear attraction matrix. So this is going to be the total attraction energy that an electron in orbitals A and B feels towards each nucleus. And the electron-electron repulsion integrals that we have to evaluate. And we'll see that these share a similar form that is significantly different from the integrals that we had to construct for the overlap matrix and the kinetic energy operator. And the reason why these are different, to understand why these are different, let's take a look at the actual Coulomb potential. So if we look at our screen here, we have the Coulomb potential for 2 point charges is just Z1 times Z2 over the distance between them, and this is written in atomic units. So if I had, let's say, a hydrogen nucleus located at point A, and an electron at some other point, we'll call this point B, the hydrogen nucleus has a charge of +1, the electron has a charge of -1. If they're located 2 Bohr apart, then we would have a total potential of -1/2 Hartree. Of course, quantum mechanically, we know that our electron isn't a point particle. We're placing it in some delocalized orbital. And so to evaluate the Coulomb operator for an electron in a delocalized orbital, we need to take a volume element of that orbital and integrate over all volume elements divided by their distance from the nucleus that they're attracted to. And so that potential energy is an integral over all space times -1 for the charge of the electron, times minus z sub a, or the charge of that nucleus, divided by the distance between the distance of each volume element from the nucleus, so 1 over r sub a, times the density of the electron, which would be rho, and we've written this as rb because we're writing all of our electron orbitals as atom-centered functions. So if I were to write this in terms of orbitals, it would be integral over to all space times minus the charge of the nucleus over Ra times phi squared b of Rb. Okay, and it's this difference, the fact that this is a function of distance from the nucleus, and we're writing our orbitals as a function of distance from some other point in space, that breaks the symmetry and makes it a little bit harder to evaluate. So let's take a look at what the actual matrix elements look like. So the nuclear attraction matrix that we're going to write is VAB. Each element, VAB, is going to be a sum over all of the nuclei times minus z sub n, which is the charge of each nuclei, times the integral of phi a times basis function b divided by distance from each nucleus integrated over all space. Okay. Alright, so if we take phi a times phi b, this is going to be a sum of primitive Gaussians multiplied by some normalization constants and contraction coefficients. For each primitive Gaussian, combination of primitive Gaussians and basis function a and basis function b, when we multiply them together, we'll get a new Gaussian centered at point P with exponent little p, which we can write as such, some normalization constant times e to the minus p r sub p squared. And we now need to evaluate this integral, the integral of some new spherically symmetric Gaussian divided by its distance from a nucleus. And we can see the trouble here when we write this in not in terms of r sub n, but as a three-dimensional or triple integral over x, y, and z. Right? We have this minus z sub n over the square root of x minus x sub n squared, y minus y sub n squared, plus z minus z sub n squared, times an integral that's centered at point P. And so we can't split this up anymore into a function of x times a function of y times a function of z. We have to evaluate this triple integral, and the question then comes down to how do we do that? And the answer to this problem is given by a British chemist named Frank Boys in the 1950s, which is we can look at this value of 1 over r and look at the Gaussian, the fundamental Gaussian integral theorem, and realize that we can rewrite pi over r sub n, oops, that should be a square root of pi, as an integral over all space times a Gaussian function of decay length minus r sub n of exponent minus r squared times t squared dt. So if we integrate over t, we get square root of pi over rn. Okay. That's a little bit interesting. If we take that and then we plug it into our integral over this Gaussian function, we get some constants out front times an integral over all space with respect to PRP times an integral with respect to T. But we can just use the Gaussian product theorem to multiply these two together. And then we get an integral over T and an integral over all space. And when we take that integral over all space, we can just use the Gaussian integral theorem to evaluate that numerically. And then we get a single function of T. And then we can do a change of variables and cast this in terms of a finite integral from 0 to 1 over e to the minus p times r squared np, which is just the distance between nucleus n and new Gaussian p, times some function u, which is t squared over p plus t squared du. Okay, looks complicated, still doesn't look easy to solve, but it turns out that there's a function related to this called the Boyce function of order n, which is the integral from 0 to 1 of e to the minus x t squared times t to the 2n dt. This looks like a function that doesn't help us at all, but it turns out there are mathematical ways of solving this in terms of power series that we can use to evaluate this as a finite number, and your computer can do this relatively quickly. Just like your computer can evaluate, say, a sine function, which we can also write as an infinite series, we can have a mathematical recipe to evaluate a Boyce function. You can look this up in a handbook of mathematical functions, say Abramowitz and Stegen. We can rewrite this Boyce function in terms of other mathematical functions, like the error function or the gamma and incomplete gamma functions. But this is actually a solvable, tractable problem, even if it doesn't look like it. And so, given this, we can rewrite this entire integral as just some normalization constants divided by an exponent times the 0th order Boyce function of this number, which is just a constant. And that is how we're going to solve for our matrix elements for the nuclear attraction. All right, so what we're going to do is we're going to write a MATLAB function to evaluate the Boyce integral. And we're going to have, for the nuclear attraction integral, we only need the 0th order. We're going to go ahead and write an arbitrary nth order Boyce function in MATLAB, because we're going to need it when we add an angular momentum. And then for each matrix element VAB, we're going to sum over all nuclei. We're going to solve over all primitive Gaussian, all combinations of primitive Gaussian functions and basis function A and B. Make a new Gaussian for each one of those centered at point P with exponent little p. And then we're going to evaluate the Boyce function f0 of p times the distance between that new Gaussian and the nuclei squared. And then when we sum all of those up, weighted by the appropriate normalization constants and the appropriate contraction coefficients, we'll have our matrix element VAB. And then we just sum over all possible A and all possible B, and we have our matrix. Okay? So the electron-electron repulsion matrix is going to be a very similar ordeal. Here, though, we're looking at the operator is what is the electron repulsion energy that an electron feels due to another electron being in a combination of two orbitals. And so we're going to need to create a four-dimensional matrix that we're going to label as G, A, B, C, and D. And that's going to be for basis functions A, B, C, and D. And we're going to need to integrate over two lengths. R1, which is the distance function from Gaussian 1, and a distance function for Gaussian 2. We're going to be integrating over R1 minus R2. So this is a double integral over all space. We can go through the same arguments we made for our nuclear attraction one, expand them a little bit, and what we get is that for each combination of primitive integrals in Gaussian function A, B, C, and D, we can make new integrals centered at point P, and new Gaussian centered at point P with exponent little p, and a new Gaussian centered at point P prime with exponent P prime. We can write a new reduced exponent for those two Gaussian functions, which is going to be P plus P prime over P times P prime. And then we can evaluate that integral as a square root of 4 alpha over pi times the Boy's function of that reduced integral times the distance between Gaussians formed from orbital A and B and Gaussians formed from orbital C and D. Okay. Again, we're just going briefly over the process of this. I strongly would recommend reading some of the literature on how to solve these Gaussian integrals, say Haugacher and or somebody else in the literature. But in the next two videos, we're going to go over how to actually implement this Boy's function and then calculate this four-centered integrals G, A, B, C, and D using our Boy's function. All right, so stay tuned for that. Cheers.